Okay, my name is Akhil. Today I'll be telling you about an explicit construction of expanding generating sets for abelian groups, also called Cayley expander graphs, and this is joint work with Moshkovitz. Let's start with some preliminaries. So we're studying Cayley graphs, and a Cayley graph is just a graph defined on a group in a certain way. So given a group G and a subset S of G, which we'll call the generating set, the Cayley graph of G with respect to S just has the group elements as the vertices and edges drawn according to multiplication by S. So if I have some little g and I want to know the neighbors of that vertex, I just multiply little g by every element of S, and that defines the neighborhood. So we're going to assume that whenever we talk about a Cayley graph, that S is symmetric and generates the group, and therefore the Cayley graph is undirected, connected, and degree regular. An expander graph is a graph which is well connected but also sparse. So we'll define expander graphs using the spectral definition. A graph G, which is deregular, is said to be an expander if there's a constant alpha, which is independent of the number of vertices, such that the adjacency matrix of G has spectral gap at least alpha. So this is equivalent to a combinatorial definition, where for all subsets of the vertices, the fraction of edges leaving the set out of the overall number of edges incident to the set is bounded away from 0. So this just means that if you take a random step starting from S, then with some constant probability you'll leave. And so in that sense, the set expands. So we're interested in expanding Cayley graphs, and the starting point for us is a randomized construction due to Alon and Roykman in 94. What they proved is, given any finite group and any desired epsilon, if you choose a uniformly random subset of the group of size log g over epsilon squared, then the Cayley graph of G with respect to S has spectral gap 1 minus epsilon. So this is a very good spectral gap, and you only need a few group elements. I mean, logarithmic in the overall group size. But this is a non-explicit construction, and we want explicit constructions because Cayley graphs are very useful pseudorandom objects. So there's actually various equivalent formulations of this object. One is epsilon biased sets, which are just pseudorandom generators against linear functions. So in fact, for any finite field, there are constructions of epsilon biased sets which are equivalent to expanding Cayley graphs, and these give not only the best pseudorandom generators against linear functions, but also against low-degree polynomials. Another equivalent definition is epsilon balanced codes. So these are linear codes over, in fact, any alphabet, where if you take a word from the code, then it has roughly the same number of symbols for all the symbols in the alphabet. So this is an even stronger property than minimum distance, and it's useful in a variety of applications. The third motivation is to have a set with some nice Fourier properties. So specifically, if you take the set S that generates G, then all of the non-trivial characters of S have small bias, specifically at most epsilon. And this implies that S is not only an expanding generating set, but also gives an almost k-wise independent distribution on the group. And we'll explain what this character term means later. So there are various applications to pseudorandomness. Expanding Cayley graphs are very fundamental, and so that motivates us to look for explicit constructions. So our result is to give an explicit construction for abelian groups. And we should say that for abelian groups, the upper bound that Alon and Roykman gave is also roughly the same as a lower bound. So if I have, this should say g to the n, but if I have an abelian group G and I take its product n times, then we know that an expanding generating set must have at least this size, which is roughly the same as the upper bound. So many previous works have tried to de-randomize Alon and Roykman for specific groups, and they've usually gotten suboptimal parameters. The best known results for abelian groups in general are pretty poor. It's something like n to the 10 over epsilon to the 10. And for general groups, it's something like n over epsilon to the 11, where again, we're talking about g to the n rather than g. So our main theorem is to get a near optimal dependence on error and an optimal dependence on dimension. And so what we show is that there's a deterministic polynomial time algorithm, which if you give it an abelian group, as well as an integer and a desired epsilon, it'll output a generating set of g to the n of size n times polylog g times epsilon to the 2 plus little o of 1 with spectral gap 1 minus epsilon. So this is almost as good as you could hope for. The best thing would be to have, instead of polylogarithmic dependence on g, to have exactly log g dependence, and to get rid of this little o of 1 term in the exponent. So how do we construct this object? There are three tools we use. So let's fix an abelian group G, an integer n, and a desired epsilon for the rest of this talk. And our goal will be to explicitly find a subset of G to the n such that it generates a Cayley graph with spectral gap 1 minus epsilon. The three things we'll use are first a sort of base set or an initial set. So this will be a generating set of G to the n, which gives a Cayley graph with some spectral gap, but not necessarily very good spectral gap. So we can think of this epsilon initial as maybe 0.99. And then the size of the initial set will be n times polylog g, and there will be some dependence on the initial expansion as well, but it's a constant, so we don't need to talk about it. Next, we'll use explicit unstructured expanders with really good spectral gap. So there are many constructions out there. The ones that we use are due to alone. And by unstructured, what we mean is that these are expander graphs, but they don't necessarily have a group structure. They don't correspond to Cayley graphs. So somehow we will need expander graphs to build our expander graphs, but these are unstructured, whereas at the end of the day, we want expander graphs that are also Cayley graphs. And finally, what we'll use is an algorithm to amplify the spectral gap of this initial set. And this algorithm is due to Tashma. It's a random walk on a wide replacement product of expanders. And we'll explain what this means in more detail, but essentially it's a certain kind of graph product. And if we take a random walk on this graph, then we can use the information from that walk to find a new distribution S such that the Cayley graph corresponding to S has the desired eigenvalue epsilon. And the size of S will be the overall size that we said in our main theorem. So our main contribution is mainly in the analysis of step 3, where we take this wide replacement product algorithm, but we prove that it works not just for the case where it was initially studied, which is F2, but also in the more general setting of any abelian group. Okay, so let's move on to the analysis of the wide replacement walk. First, we'll need to fix some more definitions. First of all, the way we define the spectrum of a Cayley graph is with respect to its characters. So a character of an abelian group is just a group homomorphism from G into the multiplicative complex numbers. And it's known that if I have a Cayley graph for an abelian group G with generating set S, then the eigenvalues are defined by taking any character and then looking at the expectation of that character on S. So the choice of S determines the value of this expectation, which in turn determines the eigenvalues. And I should note that there's always a character which maps everything to 1, and this will give you an eigenvalue of 1, which is what we know happens for any deregular graph. Next, we can also define a bias of a distribution. So if you have a random variable on a group, then the bias of that random variable is just the maximal expected value of a character, except we exclude this constant character. So this is sort of like the eigenvalues of the Cayley graph of G, but we exclude the trivial eigenvalue, and we talk about a generating set corresponding to some distribution D. So in terms of this language, what we want is an epsilon biased distribution on G to the n, which has small support size. So an initial attempt to amplify spectral gap could be as follows. Take T independent samples from your initial set and then add them up. And then I claim that this new random variable has bias which actually scales by a factor of T. So that's very good. It means that the bias shrinks very fast. But the issue is that the support size also grows at the same rate. Because if we take independent samples from our initial set, then the support size of this new distribution scales by T. And since we want a construction which has good dependence on error, and this does not improve the dependence on error, it's useless. However, that does motivate us to improve this approach by taking correlated samples instead of independent samples. And the way we'll take correlated samples is through an expander walk. So let's define another attempt which will still fail, but it'll be better than the previous one. Let's identify the initial generating set with the vertices of some expander graph gamma, and let's assume that this graph gamma has a really small second eigenvalue. So then what we'll do is we'll use a random walk on gamma to amplify bias as follows. Suppose we have some path, which corresponds to some possible run of the random walk, and then add up the elements on that path like before. Then I claim that the random variable, which is just the sum of these elements, has a small bias, and it shrinks essentially by a factor of t over 2 instead of t like before. And we'll prove why this happens, but we should note immediately that this is worse than independent sampling because we only shrink by a factor of t over 2, and we also have to pay this additional cost in terms of the expansion of gamma. But nevertheless, this is good because even though we don't shrink the bias as fast, this is more randomness efficient. And so at the end of the day, we will actually get some improvement, and it will motivate our overall construction, which is a special kind of random walk. So let's analyze this particular random walk first as a warm-up. Let's fix G to be the cyclic group of order D. In general, a finite abelian group is just a product of cyclic groups, so this example is instructive enough. And let's define omega D to just be the dth root of unity. So in this case, we know exactly what the characters of this group are. The jth character just takes an element x and then multiplies it by j and makes that the exponent of omega D. So as j grows, the character corresponding to j sort of winds around the unit circle more and more. So these are the characters of this group. And now our intuition for why the random walk should shrink the bias of our initial set is because the random walk will sort of enter subsets of the graph in a balanced way. And therefore, the distribution will be more even than whatever the initial distribution was. So let's formalize this. We're going to need a lot of notation to develop an algebraic expression for the bias. So first, let's fix an adjacency matrix for gamma. We'll call it A gamma. Let's let chi star be the worst case character for this random walk distribution. So chi star will depend upon everything else we've talked about, like the initial set, the choice of group, the graph, etc. But for the purpose of our analysis, we can just fix some worst case character and only talk about that. Let's partition the vertices of gamma into d buckets. And we say that an element x belongs to the kth bucket if it's mapped to omega d to the k by the worst case character. And so the worst case character induces this partition on the initial set. Now for each Si, we can identify a subspace of the set of vectors of length n. And we can also identify a projection operator onto this subspace. And the numbering can just be in the natural way. And then we'll define pi to be the sum of these projection operators scaled by whatever value it corresponds to. So here pi sub y is projecting onto the subspace of elements that are mapped to omega d to the y, and then we also scale that by the same constant omega d to the y and add these up. And this is for reasons having to do with our analysis. So now we have all this notation and we can very cleanly express the bias of the random walk distribution. The bias of the random walk is just a matrix norm. It's the norm of pi times A gamma to the tth power times an additional pi. So I can't prove this entirely because of time constraints, but I can give you an idea of why this is true. Essentially, if you have some initial distribution on the vertices, then the way to understand how that distribution evolves in time with the random walk is to take powers of the adjacency matrix. But for us, we want to track how often that random walk enters the buckets that we've defined. And so for each step, we need to scale by this pi matrix so that we can encode how often the walk enters each of these buckets. So when we want to analyze bias, we should actually analyze the vector pi times A gamma all to the tth power times the initial distribution u. And this will somehow capture the bias of the random walk. And therefore, if u is a unit vector, then we can bound the norm of that by the matrix norm. So if you do the analysis, then this matrix will sort of fall out, and this will be an upper bound for the bias. So how do we actually upper bound this? Well, I claim that the matrix norm that we want to bound has exactly the bound that I told you before was the bound for bias. And for the analysis, we're going to use a parallel perpendicular decomposition. So first, let's identify a one-dimensional subspace, which is just spanned by the all once vector. And then let's define its orthogonal complement to be v-perp, or perpendicular space. So then, to prove this overall bound, it suffices to prove a bound on the square of this matrix, because then we can just use some multiplicativity we can use the fact that the matrix norm is submultiplicative. So how do we prove this bound? So first we'll consider a perpendicular case. If V is a perpendicular unit vector, then actually just the first application of the adjacency matrix already shrinks the norm by a factor of lambda. And so this whole matrix has norm at most 1, and this is a unit vector, and we can bound this by lambda. The hard case is when you're in parallel space. So suppose that V is a unit vector that's parallel, and let's note that because V is in parallel space, it's just a scalar multiple of the all ones vector. So then if we use the fact that pi also has matrix norm 1, then we can analyze the norm as follows. First of all, A has eigenvalue 1, so we can get rid of this, or U has eigenvalue 1 with respect to A, so we can get rid of this A. Then we can break this up into a parallel and a perpendicular component and use the triangle inequality. For the perpendicular component, we shrink by a factor of lambda. For the parallel component, the eigenvalue is 1, and so we get rid of the A. So now we've gotten rid of A on both terms. Then what we do is just bound this whole quantity by 1, just because pi has matrix norm 1, and this is a unit vector. And now we want to analyze this leftover term. And we want to show that this is at most epsilon initial. So why is that? So here's the intuition. If we look at the structure of this pi matrix, it's essentially a block diagonal matrix where the blocks correspond to the buckets that we partition the graph into. And so you have an identity matrix here, then you have another identity matrix but scaled by a root of unity, and in general the blocks will just be scales of the root of the identity matrix times some root of unity. So now notice that if the blocks are exactly the same size, then actually pi times u is contained entirely in perpendicular space. And the reason is because if you add up all the roots of unity, you get 0. And so then if we're analyzing the perpendicular component, or the parallel component rather, that's just 0, and so the bound follows. But in general, actually we claim that most of the mass of pi times u does exist in the perpendicular space. And the reason is because we started with an S initial, which has bias epsilon initial. And so that means that the blocks have to have roughly the same size, because no matter what character you analyze the initial set with, it'll have bias epsilon initial. And therefore, because these blocks all have roughly the same size, most of the mass of pi times u will be in perpendicular space. And so the component that's in parallel space will be pretty small, and we can actually bound the norm of this vector to be epsilon initial. And so that gives our overall bound. So good. So we have a method for amplifying bias, but this is not the end of the story. And in fact, there's a very serious drawback to the ordinary expander walk. The issue is that the explicit construction we get will have a dependence of epsilon to the 4 rather than epsilon to the 2, which is the parameter that matches Ullmann-Roykman, and that's what we're after. If we wanted to prove epsilon to the 2, then we would need to show that the matrix norm bound is much better. And actually, it would need to be something like the same quantity, but to the tth power. And what that means is that you would need to show that in almost every step of the random walk, the bias shrinks. The problem is that this is just not true. So if you consider a vector u that's in parallel space, then within one step, the bias could be exactly the same, because first you multiply by a, and then the eigenvalue is 1, so u is the same. And now if you multiply by pi, then what you get is just a vector whose entries are all roots of unity. And so obviously its norm will just be 1. So the walk can get stuck in parallel space, and so the ordinary expander walk will not work. And so that motivates what does work, which is the wide replacement walk. Okay, so the wide replacement walk is a product of two different graphs. So the gamma graph is the same as before, and let's suppose it has d1. So then for some parameter s, we're going to need to find an initial graph h, or an inner graph rather, on d1 to the s vertices with two properties. First, h should be an expander, and second, h should be pseudo-random with respect to gamma. And this is actually the key idea in the analysis. Ignoring what pseudo-random means exactly for now, we can define the wide replacement product of gamma and h to be a graph that's as follows. Essentially, we replace every vertex of gamma with a copy of h, which we call a cloud. And then there are edges between clouds that correspond to the edge structure of gamma itself. So then our overall construction is, as before, you identify the vertices of gamma with elements of your initial set S, and then we take a t-step walk on the wide replacement product and output the sum of the path elements, but only the parts that correspond to gamma, because those are the ones that are actually group elements. And here's a picture of what this wide replacement product looks like. Essentially, you have your outer graph G, your inner graph H, and then you replace each of these vertices on this triangle with this path. And now you have these clouds, but then you also have edges between the clouds that correspond to the edges of G. So now let's analyze the wide replacement walk. I claim that it's almost identical to the analysis of the ordinary expander walk. So all of that work we did analyzing the expander walk will still come in handy. Let's let pi, A gamma, and AH be analogous matrices to the pi and A gamma from before. And let's write down the eigenvalues of each of these matrices. So then my claim is, if I can bound epsilon initial and the eigenvalue of gamma with respect to the eigenvalue of H, and if X is the random variable that comes from the wide replacement walk distribution, then the bias of X can actually be bounded again in terms of some matrix norm corresponding to the walk. So again, we have our pi, which tracks the membership in different buckets, and now we have the adjacency matrix of gamma and H. And this is sort of abusing notation because these aren't strictly the adjacency matrices of gamma and H. They actually operate on some tensor product space, but we'll ignore that detail for now. So then the claim is that we can bound the bias of X in terms of a matrix norm, and unlike before, the matrix norm does shrink fast enough. So if you take the S power of this product, then the matrix norm of this thing will be something like lambda of H to the S power minus some constant. And so you gain in almost every step. So how do we prove 2? So as before, we're going to use a parallel perpendicular decomposition. So let's talk about a parallel space, which is now vectors that are constant on the H component of the product, and let's define its orthogonal complement. So in the perpendicular case, this product of matrices will shrink any vector by a factor of lambda to the H. That's easy, we gain in every step. In the parallel case, we could get stuck in that space like before, but now we will use the fact that H is a pseudo-random inner graph with respect to gamma. And roughly what that means is that when the walk is in parallel space, the next S steps will approximate the ordinary random walk on gamma. And the reason is because if H is pseudo-random with respect to gamma, then it can use the entries of the walk vector at that point as a source of fresh randomness, and then it can somehow simulate the random walk on gamma, even though the walk is really happening on the product of gamma with H. So from before, we know that if we take the ordinary walk on gamma, then we shrink bias by this factor, the initial bias plus the expansion of gamma, to the t over 2th power. And we assume that this entry here was already less than lambda to the H squared. So if we plug this in, then we get that actually every S steps will shrink the bias by essentially lambda H to the S. And so we conclude that in the both cases, we're going to shrink bias fast enough, and that means that we're going to get fast enough bias amplification and hence good support size. So that's the analysis. So in conclusion, we used expander walks on a wide replacement product to amplify the spectral gap of some initial generating set for our Abelian graph. And what was crucial in our analysis was that we identified the barrier to the ordinary expander walk, which was the fact that this walk could get stuck in parallel space. And the wide replacement walk is constructed specifically to avoid this bad case by gaining even in the case where the walk is stuck in parallel space. And this uses this machinery of a pseudo-random inner graph and a wide replacement product. So now we have a construction of expanding generating sets for Abelian groups, and it raises some natural open questions. First of all, can you improve the support size of our construction? So in particular, we know that to get epsilon squared as opposed to this almost epsilon squared, we need a new technique. Expander walks won't work and they'll unavoidably pick up this extra factor. Can you get expanding generating sets for non-Abelian groups? So current constructions are quite poor with respect to parameters, and they actually also use expander walks. And so it's plausible that the same kind of expander walks algorithms could be used in that setting as well to amplify bias. There's some recent work on expander walks that fool Boolean functions besides characters. And so this work by Cohen, Perry, and Tashma actually proves that expander walks fool all symmetric Boolean functions. And we can ask what the correct generalization of this property is to Abelian groups. And finally, what are some additional applications of our construction? We list some in our paper, but there are undoubtedly many, many more because these objects that we're studying are so fundamental and so widely used that surely there have to be more than just the applications we've found. So that's it. Thank you.